Using the t-table is a little different than using the standard normal table. The reason is because for the t-distribution, you have these degrees of freedom, and what that really means is that you would have a separate table for every possible degree of freedom, and that would just kill too many trees. So instead of doing that, they only list a handful of probabilities on the t-table. So what you can't do with the t-table is you can't find something like what's the probability that t is less than or equal to some particular number like that. There's no way to do that with the t-table. What it does do is going the other way, which is if you're given the probability, find the t. So, for example, if I want to know, okay, let's say degrees of freedom is 12, and I want to know, I want my probability that t is less than t naught to be 0.90. This I can do with the table. And I can only do this for these particular nice probabilities like 0.9, 0.95, 0.8. Those are all in the table. Any other probability, there's not really anything to do. So let's do this right quick. If I pull up my t-table right quick. So I want one tail, so I'm looking at a picture like this. And I want the probability to be, well, I guess this is actually kind of opposite of what I wrote down. This would be if the tail was 0.10, then my t would be 1.356, or actually rather negative 1.356. And because, well, it's kind of silly. It's a little bit of silliness, but yeah, this is 1.356. If this was 0.1, this would be negative. The whole thing's symmetric, so this is positive. But you're not really going to do this very much. Really, all you're going to be using this table is to do hypothesis testing anyway. So let me do a hypothesis test just to kind of show you a feel for how you're actually going to use this. All right. So let's say a car is supposed to get at least 40 miles per gallon. And we take 10 cars, and we find that their average is 38, and the standard deviation is 3. And let's say we want alpha as 0.05. So the question is it possible that these cars really do average 40 miles per the gallon and we just got a bad batch of 10 cars? Or does this 10 cars show that no, these cars really don't get 40 miles to the gallon? Well, the null hypothesis is that mu is bigger than 40, which means our alternative hypothesis is mu is less than 40. So our picture, well, you always draw the picture for the alternative because that's the one we're trying to get or not get. So it looks like this. So we're doing a left tail test. And we know it's a t-test because our sample size is 10, which is less than 30. So we're doing a t-test, and the degrees of freedom is always 1 less than the sample size. So it's 9. So right now we can already look up the table. I mean, this is all the information we need. We don't need the 38. We don't need the 3. All we need to do to look in the table is we need this degrees of freedom. Alpha is 0.05, and we're doing left-tailed. So let me pull up the table again. So degrees of freedom is 9. We're doing left-tailed, so it's going to be minus whatever it says. So 1 tail, 0.05, 9 degrees of freedom is right there. 1.833. Oops, didn't mean to do that. Doesn't matter. So our critical value of t is negative 1.833. And now all you do is just figure out your test statistic and decide, hey, is it over here in this rejection region or is it not? Well, our test statistic for the mean is over S over root n. So this is 38 minus 40 over 3 over root 10. And grabbing my calculator right quick. This is negative 0.21. That doesn't sound right. Let me do that again. Okay, yeah, sorry. So decimal to correct. Ironically, it's off by a factor of 10. 2.1. Okay. So negative 2.1 is, this right here is negative 1.8. So sure enough, negative 2.1 is over here. So sure enough, we do have enough evidence to say, yeah, there's no way that these cars really should average 40 miles per gallon. The fact that we got 38 for 10 cars is too much of a discrepancy. So, all right, that's how you use the t-table.